Oh, something about booms. I don't remember. There's a new brain rot thing. Something. Can I get? Yeah, I don't. What does it come from? Is it inappropriate?
No, it's on the cost. It's like a father and son duo. That's all it is.
Okay.
It's like
Cool.
rating stuff or something.
Yeah, like Costco stuff. They're big about Costco.
Okay. All right. So, today we are going to start chapter 6, section 3. Just so you guys know, there are 4 sections this chapter. So we'll go through all this. We're about halfway there. I think it's fair game that we could have a short quiz at the end of this section because this has been kind of a long chapter with a lot of chemistry stuff. We need to be able to check. Cool. So, in 6.3, there's something on Earth that is really, really common. What's the name of our planet?
Earth.
You're right. What do we call it as a name? It's the what planet? The blue planet. Why do they call it the blue planet? Water. Because when we took the first pictures, the astronauts took the first pictures of the Earth. It was just a big blue ball floating in space, which makes sense because the water reflects blue light. Okay. Is water special?
Yes.
Why?
We need it to survive.
So why? What? Okay, so we're special, and by inherently, water's special. I'm okay with that. There's a lot of water on Earth. Is there water on other planets?
No.
Oh yeah, Uranus.
Okay, and Uranus, I don't think there's a ton of water because it's a gas planet. Mars, is there water on Mars?
No.
Yeah.
Wait, there is?
That's a question for you.
Nope, there is. There is water on Mars. Now, when I say water, what do you think of? And that's a weird question. Don't just answer water. What's it look like? What's it feel like?
Liquid.
It's liquid. Why?
You know, cause water can be everything.
Is it always liquid?
Could be solid.
Can be water.
Can water be solid? I've seen solid
Yeah.
water.
Ice.
Oh, ice. Can it be gas?
Yeah.
Yeah. Steam.
Oh my, steam. Yeah, like water is really special because it does a few things. One, it exists abundantly on this planet in all 3 forms. Now there's a 4th form of matter out there that's not liquid, not gas, not solid. You guys know it? Plasma is, I just spit when I said that. Not on you, I hope. Plasma is the 4th state of matter. The sun, you guys ever heard the sun is on fire? Like it's a big ball of fire?
Yeah.
Not true. The sun does not burn. That's not fire. What you're seeing is a nuclear reaction. You're seeing plasma. That's what the sun is, a big ball of plasma. Okay, now, water, it turns out, is super duper important, and it does a lot of unique stuff that other compounds don't do. And it's so important to us and every living animal on this planet because, for the most part, 70% water or more for us. But water and its solutions is our focus. Now, when we talk about solutions, we will define this here shortly. I will try my best to write it every time, but just so you guys are aware, SOL''N will probably sneak out as my shorthand. It's my lazy contractions. I just cut out the ocean part. So that is solution, SOL''N. That's my shorthand. Okay, now looking at it, right off the bat, there's some big questions, and I'm just going to throw you a big reminder. Molecules are something specific. Molecules are when you put atoms together and they share their valence electrons. Okay, molecules are covalent bonds. That's all that means. They share electrons. So with that in mind, what's water made of? It's made of 3 atoms.
Oxygen.
So oxygen, there's 1 oxygen and 2 hydrogens, H2O, and they stuck together by sharing electrons. Okay, that's easy to deal with. Now, there's a natural question that comes up in my mind. Why do they stick together? Like, one, water is fine. Like, I'm okay with saying, hey, they attract, they share electrons, they're stuck. But you ever tipped a cup and saw a piece of part of water come out?
Yeah.
Does more water keep pouring and like seemingly it makes a big long line? So do you agree then that it seems maybe not super strong, but water sticks to water? Like if I had a water molecule here and a water molecule here, they stick together and they form a liquid or a gas, depending, or a solid, whatever the temperature might be. But why would it stick together is a pretty natural question if you've ever gone just a step further. So, sounds fancy, it's not. We are looking at inter, and this is not going to be a definition. So inter just means between, so inside, right? And water is a molecule, just means covalent bond. So when we see this scary word, intermolecular, sounds terrible, but in molecules. That's all that means. Intermolecular forces are what we're focusing on today. So the question at hand starts to become, how does one little molecule of water, a single H2O, and another H2O, why do they stick together? Like, that's what this is really addressing. So right off the bat, we know that, and maybe you didn't remember, this is a covalent bond. Covalence means that they share their electrons. Everybody cool with that? Now, if I draw a small picture here, and I'm going to make oxygen blue for no particular reason, and I think I can just do this and just shade it. We're going to see if this works or not. There's my, yes, there's a water, or almost a water. That's an oxygen. You guys should draw this for me. Here's an oxygen, O, and I'm just going to put ox for oxygen. Now, right now I just have a single atom of oxygen there. To make it water, it must have two what stuck to it somewhere? Hydrogen. Okay, so check it out. We'll do the same thing. I'm going to use this, and I'm just going to say, look, there's a hydrogen here, and there winds up being another hydrogen over here. I'm going to use red for hydrogen. I don't care if yours are colored or not, but I will just go ahead and label these H and H. There's a water molecule. Okay, nothing crazy about it. It's H2O. And this is really how they look. They have that weird Mickey Mouse shape. It's just upside down the way I've drawn it. Okay, now looking at this, they share electrons. That hydrogen shares, each hydrogen shares an electron with oxygen. Now, these aren't perfectly to scale, but hydrogen is only 1 proton. That's all that's in the middle. Oxygen is 8. Do you agree that oxygen is bigger? Like, one, it has more mass because there's 8 protons instead of 1. So I know that physically it would weigh more, 8 times more at least. But beyond that, it's also physically bigger. Like, literally, it's a larger atom. Which means, this isn't really the truth that's happening, but I think it's a good analogy. If these were like planets, which one has stronger gravity?
The oxygen.
Oxygen. Okay, in the exact same vein, oxygen, more protons, more positive charges, means it pulls harder on a negative charge. Everybody okay with that idea?
Yeah.
More positives pull more negatives. So what this means to us is that even though these share electrons, this statement super important. Although electrons, and what's the shorthand for electrons? E minus or E negative. Although the electrons are shared, and they are shared, that's what it means to be covalent or a molecule. Even though the electrons are shared, who pulls harder on the electrons?
Positive.
So let's not use, you're right, that positive pulls on negatives. I agree with you completely. What pulls harder or has more positive charges, an oxygen or the hydrogen? I'm going to remind you, hydrogen has 1 single proton. Oxygen has 8. Those are my positive charges. Oxygen has way more positive, right? So, although the electrons are shared, oxygen pulls harder. Now, they have to share them, and when I talk about it, it sounds like this nice altruistic, they all want what's best for everybody, and they do, they want to be stable, but just inherently oxygen pulls harder on them, which means the electrons wind up spending a little bit more time closer to the oxygen than they do the hydrogen. Just like our moon spends more time close to us than the sun because we pull harder on the moon than the sun does. Okay, oxygen pulls harder. The reason that this matters is, don't add these. I'm going to use these obnoxious dots for my electrons. When we drew these the first time, and we said, hey, here's the shared electrons between them, and that's how we drew it out, right? Now, there's some physics in here that I'm just going to really quickly gloss over. That isn't the main point of the lesson. We never really know where an electron is. Like, they're not in a specific location. They're this area where they probably are, which is a weird idea. In reality, this picture would look more like this, where these oxygens, or these electrons, are pulled closer to the oxygen. Now, don't draw that part, Fred. I'm going to make a comment that symbolizes this. All I've done is I've moved the electrons to show they're closer to the oxygen. Now, the fact that the electrons are closer to the oxygen means that rather than being completely balanced charge-wise, the oxygen gets a little bit more negative because it pulls the electrons closer. Does that seem reasonable? If my negative charges instead of being shared here, kind of drift up. They're closer and more involved with oxygen. Which means we get something really special about water that happens, and this is huge. When oxygen pulls harder, couple things that this means. You can write it down here, or I'm just going to draw it right here. This charge then, up top, even though they're balanced, is a slight, and if it has more electrons closer here, is this going to be slight negative or slight positive? Which one's negative, electrons or protons? So oxygen now has most of the electrons. They're shared, but they're physically closer. This is a slight negative charge up on top of this then. Now, in a similar vein, these things are neutral charged overall when we talk about the covalence part, because proton and electron, whatever, that's fine. If the electrons got pulled up here and made this a little bit more negative, what had to have happened down here if it now lost a little bit of that electric charge, that negative charge? If these were balanced and they lost a little bit of negative, or you subtracted a negative, what happens in math when you do that? It's positive, right? So we see on the top near the oxygen, we get a slight negative. Down here on our hydrogens then, we're going to get a slight what? Perfect. Not sight, but slight. Okay. This is going to feel unrelated, but I think it's a fun question. Have you guys ever touched a magnet?
Yes.
Okay. Now, I hate the language that we use for them. I'm going to use an old school magnet here just to show you. This magnet that I'm holding up on the board, or up in front of you guys, it has two colors on it. Why?
Positive and negative.
So I love that language. That's not the standard language, though. North and south is what we use on magnets. Positive and negative makes way more sense. Okay. If I were to cut this magnet in half, what would happen?
They're gonna attract each other.
You think so?
No, they're going to
Oh, they're gonna
go
avoid
against
each
each
other.
other.
So here's a weird thing, and I'm not going to cut this magnet in half to demonstrate this. But this magnet, do you agree, has a side that's north and a side that's south? Okay, it's charged. It doesn't matter how I hold it. Like, it's not a true direction. It's just what we call that. Okay, if I cut this in half, I now have two magnets, and they each have a north and a south. Like, it's just two magnets. It would just be split. You can't make it with one charge on it, which is just a weird idea. That might not have clicked for everybody. We'll look at that eventually. Cool. Why did I feel the need to discuss that real quick?
Just for fun.
Oh, well, everything I do is for fun, but I don't remember the point. Is our planet magnetic?
Yeah.
We have, what do you call the regions on Earth where all the magnetic fields come from? And that's a big question, but I guarantee you know it. Oh my goodness, the what?
Oh wait, it is.
Oh yeah, say it louder.
The North Pole and the South.
The North Pole and the South Pole. Okay, when you see the word pole show up, it comes from magnets. Our planet is a big magnet. We're not going to go into that because this isn't Earth science. But there is a side of our planet that generates north magnetic fields, or positive, whatever you want to call them, and a side of our planet that generates negative or south magnetic fields. Okay, opposite ends, different charges. What do you notice about this new atom right here, or this new molecule? Does it have a north pole or a positive pole and a negative pole?
Yeah.
Like very clearly, right? Up top is positive or negative in this case. Down south is the opposite. Now, looking at this idea is a way to talk about one of the key features of water. We're going to sneak a definition in here. And it turns out that what we're talking about, because I can see a very clear positive and negative pole, is we're defining a polar molecule. Now, by definition, we're just going to say molecule or covalent compound. I would use the word molecule, but this is a good review. A covalent compound with a difference or a different charge at each end. Now, water is a polar molecule, and we've seen that oxygen pulls a little bit harder. This is really unique. Why would I care that this is true? Now, I'm going to ask you guys to discuss this to give a little bit of guidance. You don't have to draw a bunch of these, but I'm going to put a bunch of waters on here, and I'm going to get rid of the writing. Whoa. And I want us to think about it, but I'll give you a picture to kind of discuss here. So, I hate it. Just to make it a little bit easier, all I'm going to add to this is I'm going to write a plus sign down here because I know that they're positive down here. That's a positive pole, and here's a negative pole. Okay, everybody good with that? So, with the class rather, right? Because we just have a small class. Why is this important is a question at hand. And check it out. Here I have some water happening, and I didn't spin them. If I wanted this water, all of a sudden it gets introduced, and it goes, hey, I'm here. Is it going to stick like this, you think?
No, it's gonna connect from the bottom to top.
What do you mean? So where should I move this one?
On
That one is on the top.
On the top here?
Yeah.
Now, turns out either answer would have been fine. Why did you make that determination?
because the red, like it feels like it connects.
It feels like it connects. I'm okay with that, but I think we can get a better one. Instead of just saying it feels like it connects, what do you know that the north and the south side of a magnet are going to do? Are they going to repel or are they going to attract? They're going to attract. And we have essentially an atomic magnet in front of us. Does it make sense that the negative side of this connects to the positive side of this? Now, these are exactly like magnetism. Now, it's pushed to a really small scale, and there's some fancier stuff going on. But if I add more water, so here's another one. Is it going to keep doing this? And it's going to keep doing this in a lot of different ways. I can't draw three-dimensional, but if I have a ball here that's all positive up here, maybe I stick a negative on here, and like they can join on everywhere, right? So what we wind up seeing by this polar idea is that water molecules bunch up together, and they attract each other specifically. Everybody cool? Magnets, they attract, that's what's happening. Now, to expand on this, it turns out that there's a lot of places in our world, and specifically in biology and such, where this has an impact. Without reading, I just want your guys' thoughts. Why would any animal, maybe they don't like mentally care about it, but how would the fact that water sticks to water, which is a weird idea, but that's what we're seeing, how would that impact something that's alive on our planet? Why would it matter that water sticks to water? Talk it out as a class. Anyway, the fact that that water sticks together allows those bugs to walk and live on the top of the surface. There are other situations where this works, but it's that attractive force between these two that stick them together that allows that to happen. Yes, sir?
Can I get the top part?
Yeah. Now, as we look at this, we're not just going to call this magnetic force. That's essentially what we're seeing happening. Anybody here speak Dutch? Dutch? So, yeah, not, hold on, not Red Dead, not the harbor that we're in, but the language Dutch. Probably not. Do you know any Dutch names? Okay, so Dutch is essentially, and this is, if I were a language teacher, I might not make this comment, but I'm not a language teacher. Dutch is like changed German. Like they're similar, they have the same roots. So if you speak German, you can probably understand some Dutch. The reason I'm asking that is because all of this, the science that goes into this, the chemistry, the physics, was discovered by, I can't remember his first name, but I'm going to ask somebody to go ahead and pronounce this for me here in just a second. Oh, so that's a Dutch name. Vanderlicht? Absolutely, that is a Dutch name. How would you say this? I don't care who goes. Van der Waals. Okay, yeah, it's just a V noise. Van der Waals. Okay, turns out that instead of talking, magnetic forces, because essentially that's what we're doing, Van der Waals forces are what we're really seeing at work here. So, right off the bat, Van der Waals forces apply directly to water. There are other things that they apply to, but the fact that water has a positive and a negative end, we call it a what sort of molecule?
Neutral.
Nope. Look at your notes. Just like our planet has a positive and negative for a north and a south. Poles. This is polar molecule. Van der Waals forces are the following. Turns out that anytime you have a polar molecule like this, whether it's water or not, the negative end should attract to the positive end. Like, that's just, I don't want to say obvious, but that's how magnets work, and that's the analogy I'm using. We're just going to say that these forces are the attraction between the ends or I'm going to say the poles of polar molecules. Anytime that you get this positive and negative charge at the end of a molecule, these poles, they're going to attract. And this is just, instead of calling it magnetics or magnetic attraction, we're going to call it by its real name, van der Waals forces. Okay, looking at these vary depending on how polarized these are, so how negative and how positive each end is, that impacts it. The shape of the atom also matters though, because if I have negatives coming out of every direction, then I can join on in all those spots and I get more forces acting. Okay, with these, we've already seen water striders, those bugs that live on the top of water. I've never lived somewhere where they exist like naturally. You guys ever seen a gecko in real life? Okay, where would you see a gecko? You might see it on the ceiling, which I have been to places where this happens, and it's weird. Where I'm from, spiders are the only thing you find on the ceiling, but I would argue, and I would bet that van der Waals forces are also present there. How do geckos stick on stuff? So let's check. You ever seen a close-up of a gecko's foot? Interesting.
Wait, I think it was in here.
I think it's in your book too, but we're going to show it. So, here's a gecko's foot. Okay, it looks like this. And if you zoom in further, it even looks like this. It looks like a bunch of little hairs sticking out of it. Okay, gives Bam Bam the heebie-jeebies apparently. I'm cool with that. Now, as we look at this, when I was a little kid, I thought it was like little suction cups. Seems natural, but I've seen lizards stick to ceilings that suction cups wouldn't work on. So what's really happening here is we get polarized molecules here that take advantage of the fact that everything realistically has a little bit of polarization to it. Some of it is really, really tiny. We don't really take advantage of it. But these work using those van der Waals forces and the attraction between the atoms at the end of those little hairs on a gecko's foot and the atoms that form up the surface that they're walking on. Whether it's a wall, whatever, small van der Waals forces are responsible for this. Now, the stickiness, that idea, yeah, there's nothing physically sticky about it other than the attraction between the polarized molecules. Cool. Now, back at it. It turns out that these things, surface tension is water striders, but that's van der Waals forces that cause surface tension, and things like that. When we look at these, as we think about these forces, if we think of covalent bonds, how they're actually stuck together, it's really hard to break the hydrogen off of an oxygen. The forces that hold those atoms together, that connect the hydrogen and the oxygen, they're super duper strong. The forces that hold this this water to another water are much less strong. We can break those easily without using anything fancy. I can break it, surface tension, without much issue. Check it out. In here, there's water. Is there surface tension? Like if a water strider were in here, which there's not right now, but if a water strider were in here, it'd be standing on the top, right? There are van der Waals forces holding this water together on top. Have you ever seen somebody break a van der Waals force? You're about to.
Oh yeah.
Did I just break that surface tension?
Yeah.
I was able to do it. Could I do the same thing and actually pop the hydrogens off of this oxygen though? No, that's much stronger of a connection. Now, other than knowing that they exist, I'm not super worried about it. We're cool there. Furthermore, everybody feeling all right so far? This is pretty deep physics and chemistry. Am I going too deep into it with, like, we're talking pretty deep? Okay. All right. So, within these, we need to talk about those van der Waals forces hold molecules to other molecules. Water sticking to water is a van der Waals force. Now, the specifics of how the oxygen and the hydrogen stick together, this becomes a whole class that winds up being really, or a whole idea that winds up being really important, and there's specialized classes for this. When we talk about how things form, one of the common way that atoms connect to one another, especially any atom that contains hydrogen, like water, for example, is a hydrogen bond. Now, as we look at this, super easy. There's a few things that hydrogen really likes to hang out with. And again, remember, to my knowledge, hydrogen doesn't really like or dislike anything. It's not sentient. It doesn't have feelings, I don't think. But hydrogen bonds, easy to find. These are the weak interactions or attractions, but I'm going to call it interaction here, between Any idea on which atom we must have to have a hydrogen bond? Which element from the periodic table is going to be present in every hydrogen bond?
The H.
It could be, oh, the hydrogen. That makes sense. Yeah, they all have hydrogen. And Andrew, love what you said, so I'm just going to use that. I'm going to write H in brackets like this, indicating it's what? Hydrogen. If you need to write the word hydrogen, please do. Okay, hydrogen bonds are the interactions between hydrogen and, there's a few things that hydrogen forms these bonds with. I'm going to use a colon because we get 3 different elements. I will write the letters and the names for these. First one, we get F. And then I'll label them down underneath. So it connects with whatever that is. It connects with O, whatever element this is. And it connects with N. Now, this isn't our major focus, but I think the more exposed you are to chemical symbols like these, the more natural it's going to feel when you see it again. H is for hydrogen. Got it. F is for, that one's harder. You will find it in your toothpaste. Yeah, I'll call it that. I'm fine with fluoride. It's really fluorine, but I'm good with it. Fluorine. Ooh. Am I backward? Nope, that's how it's spelled. Bugs me. Okay. O is for oxygen. So hydrogen can bond to fluorine. Hydrogen can bond to oxygen. Or N for nitrogen. Nice job, Fred. Nitrogen. Okay. Hydrogen bonds exist between these. Now, turns out, I'm just going to make a little comment. For these, this is just simply a specific type of van der Waals forces. A specific, there we go, type of van der Waals. Okay, so these attractions between them, because of the way these molecules join together and polarize themselves, they all attract to each other, and they're van der Waals forces that are the cause of that. Now, we're going to sneak in a couple different things. Have you ever heard the word cohesive? So not necessarily in the realm of chemistry, just cohesive. I am part of a cohesive group. Okay.
I think of like car material, like when you're fixing something like a base cohesive.
You're close. And I think you're just mixing it up with another word. I think. I could be wrong. I think you're thinking of the idea like tape. So, like, if I tape something, do you know another name for tape? Like, that Scotch tape is what that's called, just that roll of tape, right? That's an adhesive. That's my guess on what you're thinking of. Now, it turns out that this hydrogen bond, which is just this fancy van der Waals force, this is responsible for a couple different things that we see with water that's pretty cool. This is responsible for cohesion, and adhesion. Now, an adhesive. If you ever hear that word, tape is an adhesive. Glue is another adhesive that's really common. With that in mind, what does adhesion, do you think, mean? Knowing that tape and glue are both adhesive. Stick. Okay, if I talk about water sticking, that feels like a weird idea because water is not particularly sticky. But we just talked about the polarity of water, the charges on either end, and we don't usually use it with magnets, but water molecules, they are adhesive toward one another. They stick to each other, for lack of a better word, due to the van der Waals forces. Okay, what about cohesion? That's a harder one. So collide is a good thought. Cooperate, I'm fine with that. So they stick together in groups specifically. And we might have seen this already, Andrew, in fisheries, but I'm going to show you something wild, and this is going to be where we end today. Okay, Andrea, if you're watching this, it's a YouTube video, and it makes these videos huge if I record it, so ask me about it, and I'll show you too.